Hello and welcome to this Dr. Frost Maths video on Key Stage 5, the product, quotient and chain rules. Now these different rules are going to allow us to differentiate more complicated expressions. And there's three different mixtures of expressions we're going to see. We've seen in the past composite functions where you have a function within a function. And what I mean by that is you have a kind of expression within an expression. So we can see we have this outer expression which is sine of something. That's a kind of outer function. And then we've got this inner function, this inner expression x squared. So we'll see how to differentiate that first. What about if we have a product of two things? So we have some function f of x times some function g of x. For example, if we had x times sine of x. So how do we differentiate a product? And finally, how do we differentiate a division of two functions when we have one expression divided by another expression? Now, for composite functions, we're going to use something called the chain rule. For product of two functions, we're going to use something that's unsurprisingly known as the product rule. And for the division of two functions, we're going to use something called the quotient rule. Quotient is just a fancy word for division. Now the chain rule is probably the hardest, but it's going to be the one that I'm going to start with. And it works like this. So let's just take this first example. And we've got x cubed plus 2 to the power of 5. Now the way we differentiate it is to do the outer function differentiated times the inner function differentiated. So let me write that down for you. And I'm going to call it something called the blah rule. You'll see what I mean by that in a second. Can we see that the outer function is something to the power of 5? That's like the outer expression here. And I'm just going to say blah to the power of 5. So we want to do the outer function differentiated. Well, what does blah to the 5 differentiate to? Well, we know that blah to the 5 differentiates to 5 blah to the 4. But instead of the blah, I'm going to actually write what that blah was. And then we times by the inner function differentiated. So the inner expression here is that x cubed plus 2. And we know that x cubed plus 2 just differentiates to 3x squared. And if we simplify that, well, we've got the 5 times the 3x squared is 15x squared. And then with that, x cubed plus 2 to the 5 after it. We don't want to have any time symbol in our simplified expression. I'll just do another one of those quickly. Let's just say I had y is equal to 3x squared plus x to the power of 6. Now, the outer expression here is something to the power of 6. Let's call that blah to the 6. So we differentiate that outer expression. Blah to the 6 becomes 6 blah to the 5. And then when we differentiate the blah, because we times by the inner function differentiated, that differentiates to 6x plus 1. So we just get that. Let's apply that to this second expression here. We want to differentiate the square root of x squared minus x. Now can you see the outer expression here is the square root of something. So there's the square root of blah. And then the inner expression is this x squared minus x. Now, in order to differentiate this square root, we want to write this as a power first. So that's x squared minus x to the half. And then we can use the chain rule. So the outer function is blah to the half, which differentiates to half blah to the minus half. And then we differentiate that blah, the inner expression differentiated, which is 2x minus 1. And there we go, we've done it. And by the way, the formal way to write the chain rule is this. This is the chain rule. dy over dx is dy over du times du over dx. Now you never have to use the chain rule written in this way, but the u here is effectively the blah. So when we want to differentiate expression, we differentiate the out expression in terms of blah. So we differentiated the square root of blah, that's this bit here, and then we differentiated the in expression, the x squared minus x. So if the x squared minus x is the u, we differentiate the x squared minus x with respect to x. So that's the in expression differentiated, and that's the outer expression differentiated. And this form of the chain rule will be useful when we get on to connected rates of change, but don't worry about this form for now. What about c? So we've got sine of x plus ln of x. And I should point out, by the way, that I am assuming that you have watched my videos on differentiating trig functions and logarithmic functions as well, and exponentials and trig functions. So let's differentiate with the chain rule. Well, the outer expression is blah squared. So blah squared differentiates to 2 blah. And then we've got to differentiate the in expression and times by that. So sin x plus ln x differentiates to cos x. And the ln x differentiates to 1 over x. And there we go, we are done. What about d? We want to differentiate ln of cos x. Well, we know that the outer expression of ln of blah differentiates to 1 over blah. And then we times by the inner function differentiated, so the cos x differentiates to minus sin x. Now, if we put that over 1, we can see it's minus sin x over cos x. And that is just minus tan of x. So ln of cos x differentiates to minus tan of x. What about the next one? And this was actually an exam question once. We want to differentiate ln of x squared plus 3x plus 5. Well, ln of blah differentiates to 1 over blah. And then we times by the blah differentiated, which is 2x plus 3. But when we times by the 2x plus 3, we might as well just put it at the top. So it's 2x plus 3. So we can see more generally, when we differentiate ln of an expression, the inner expression differentiated goes at the top, and the original expression within the ln goes at the bottom. So if I write that as a general rule here, when I differentiate ln of f of x, so some expression in terms of x, I get the derivative at the top over the original function at the bottom. And this is not a standard result you need to remember. You can, as long as you know how to apply the chain rule, then you can just do it from scratch. What about f? I want to differentiate sine squared of x. Now, I explore these more in a different video about differentiating trig functions, but here's the way you do it. If you ever have a power of a trig function, always put the power outside a bracket first. So sine squared x just means sine of x all squared. And now this is in the form that we're used to differentiating. So, using the chain rule, blah squared, the outer function, differentiates to 2 blah. And then we times by the inner function differentiated, sine of x differentiates to cos of x. And if you wanted to, you could write that as sine of 2x using the double angle formula, but I'm not going to do that here. What about g? When I want to differentiate sine of 2x, the outer function is sine of blah, which differentiates to cos of blah. And you times by the blah, the 2x, differentiated, which is just 2. And if you've seen the standard result before, sine of kx differentiates to k cos of kx, which is what we've got here, it's just using the chain rule. So in fact, it's not really a standard result at all, as long as you just remember how to use the chain rule. H e to the 3x. Again, you might remember that e to the kx differentiates to k e to the kx, so it's going to become 3e to the 3x. But using the chain rule, e to the blah differentiates to e to the blah itself, and then we times by the blah, the 3x differentiated, which is 3. So that's why that works. What about I? E to the x squared. E to the blah differentiates to e to the blah. And then we times by the blah, the x squared differentiated, which is 2x. J, we want to differentiate 1 over 1 minus 3x. Now, we should write this as a power first, so we want to differentiate instead 1 minus 3x all to the power of minus 1, because the power of minus 1 would do 1 over that. So when you differentiate that, well, blah to the minus 1 is minus blah to the minus 2. That's the outer function differentiated. And then we times by the inner function differentiated. 1 minus 3x differentiates to minus 3. And if we simplify that a bit, that becomes 3. And we could write over 1 minus 3x all squared, because that's what a power of minus 2 means. And then finally, k, when we differentiate ln of 3x, we use a chain rule. Well, ln of blah differentiates to 1 over blah, but then we times by the blah, the 3x differentiated, which is 3. But 3 over 3x just differentiates to 1 over x. And we saw in the video on differentiating log functions and exponentials that when you differentiate ln of kx, you ignore that k, the number in front of the x, it still just becomes 1 over x. Now, a second principle here, find the gradient of x equals this expression here when y equals 1. But we want to find dy over dx, not dx of dy. We're used to having y in terms of x, aren't we? But here we've got x in terms of y. So if we write that, if y was in terms of x, then we could find dy over dx. But because we have x in terms of y, we're instead going to initially find dx over dy. So how do we do that? Using the chain rule, blah cubed, the outer function, differentiates to 3 blah squared. And then we times by the inner function differentiated, the blah, 1 plus 2y differentiates to 2. And if we simplify that a bit, we get 6 1 plus 2y cubed. Now, if we know dx over dy, then to find dy over dx, believe it or not, you can sort of think about reciprocating this. We've flipped this, we've reciprocated it, that's the same as 1 over it. So we do the same to the right hand side. We do 1 over 6, 1 plus 2y cubed. So in general, dy over dx is equal to 1 over dx over dy. Now that might seem a bit hacky. Why can we just treat this as a fraction? And I'm not going to go through the proof, but you can prove this using the chain rule, which I do in my slides if you do want to see that. Now we haven't quite finished the question. We want to find the gradient dy over dx when y is 1. Now we've got this expression in terms of y, so when y is 1, that means the gradient dy over dx will be 1 over 6 times, or 1 plus 2 times 1, that's 1 plus 2 is 3, 3 cubed, and 27 times 6 is 162, so it's 1 over 162. So just in summary, if you want to find dy over dx, but you have x in terms of y, then you need to find dx over dy first, and then just reciprocate it to find dy over dx, just do 1 over it. Now, in question 3, we've now got a product of two functions. So we've got x squared times sine x. You've got a product of two expressions, and you have to use something called the product. And the product rule is this. If I have y is equal to two expressions times by each other, let's call them u and v, then dy over dx is u dv over dx plus v du over dx. And to put that into words, basically, if we've got a product of two expressions, we do one of the expressions times the other thing differentiated. So we leave this u alone, but differentiate the v. And then we do it the other way around. So we leave the v alone and differentiate the u. So v times du of dx. And then we just add those two different combos together. So if we apply it to this first one, y equals x squared sine x. Let's try and do this all in one go. Well, we keep one of them as it is, let's keep the x squared as it is, but differentiate the other thing. So x squared times the other thing differentiated, cos x, and we add the other way around. So we keep the sine x as it is, so sine x stays as it is, and you differentiate the other thing. So the x squared differentiates to 2x, and that is the result. What about b? Y is equal to x root 2x plus 1. Again, we have a product of two things. Now this time, because I'm going to have to use the chain rule combined with the product rule, I'm not going to try and do it all in one go. I'm going to write the u and the v out. So this can be the u, this can be the v. So the u is the first thing, the v is the second thing. So let's write that as 2x plus 1 all to the power of a half, because a power of a half means square root of. And then let's find d over dx and dv over dx. So d over dx is just the x differentiated, which is just 1. And the dv over dx, we have to use a chain rule here, because we've got a function within a function. So the outer expression is blah to the half, which differentiates to half blah to the minus half. And then we times by the blah differentiated, which is 2. And we can see that half times the 2 is just 1, so we just get 2x plus 1 to the minus half. And now to differentiate, we use the product rule. So do you remember, we keep one of the things undifferentiated as it is, but times it by the other thing differentiated. So we're going to do the x times this thing here. And then we add the other way around. So we keep the v as it is, so this is going to stay as it is, but we times by the u differentiated, the other thing, the first thing differentiated. So that's just going to be 2x plus 1 to the half. Now if we wanted to get this as a simple expression, well, if I had, say, I don't know, x cubed plus x squared, and I asked you to factorise that, well, you'd say, well, I can factorise out x squared. And the reason you're saying x squared is a common factor is because the 2 is the lower power. Now, what's the lower power out of these two things here? Because we clearly have this common factor. This is the power of minus half, this is the power of a half. Well, the lower index here is the minus half. So we're going to factor out 2x plus 1 to the minus half. And then let's just see what we have left. Well, 2x plus 1 to the minus half times what gives you this? Well, you just need an extra x. Plus, now 2x plus 1 to the minus half times what is 2x plus 1 to the half? Well, we can see that the power's gone up by 1, so we're going to have to times by an additional 2x plus 1 to the 1. Because if you think about it, by laws of indices, if we had 2x plus 1 to the minus half times 2x plus 1 to the 1, the minus half plus the 1 is half, and that will give you the correct power. And now you can see we can just simplify the contents of this other bracket here. I didn't really need to use square brackets there. That's just 3x if we collect like terms plus 1, and that's as simple as you could get it. If you wanted to, you could write this as 3x plus 1 over the square root of 2x plus 1, and in fact I'm going to do that. But this expression would be absolutely fine. What about the next one? X cubed times 2 to the x. Now, each term is simple enough that I'm just going to do it all in one go again, rather than having to write out the u and the v and doing it in full. So we keep the first thing as it is, but times by the second thing differentiated, so 2 to the x ln 2. If you've forgotten how to differentiate exponential terms like that, then do look at my video on that. Plus the other way around. So we leave the second thing alone, the 2 to the x, and differentiate the other thing. So x cubed differentiates to 3x squared. And if we wanted, we could factorise some stuff out. So I'm going to factor out the 2 to the x and the x squared as well, and what we're left with. So here we need a ln 2 and an extra x, and here we've already got the x squared and the 2 to the x, so we just need a 3. There we go, that's as simple as you can get it. And by the way, it doesn't matter what way you add these around. So you just differentiate one of them, doesn't matter which, and leave the other alone, and then add the other way around. But it doesn't matter which way you add those. And then d, we want to differentiate 1 over 2x sine x. Now you could do this. You could write this whole denominator to the power of minus 1, so 2x sine x in brackets to the power of minus 1. Or if you wanted to, you could just realise that this is 1 over 2 times 1 over x times 1 over sine x. Because you can see, if you were to multiply those fractions together, 1 times 1 times 1 is just 1, and 2 times x times sine x is 2x sine x. And now I'm going to write this as a power. So this is half. We've got x to the minus 1 and sine x all to the power of minus 1. So I'm going to use the product rule here, because I've got a product of two things. This here is your u, and this thing here is your v. So I'm going to write them out separately. I'm not going to try it and do it in my head. There's going to be lots of chain rule here. So du over dx, that's just half times the minus 1, which is minus half, reduce the power by 1. So that's relatively easy. And this one, you will need to use the chain rule. We've got something to the minus 1. Blah to the minus 1 differentiates to minus blah to the minus 2. And then you times by the blah differentiated, which is cos of x. And let's put this all together using the product rule. We do this thing undifferentiated times the other thing differentiated. So we're going to get minus half x to the minus 1 sine x to the minus 2 cos x, and then plus the other way around. So the v undifferentiated times the u differentiated. So that is going to be minus half x to the minus half sine x all all to the power of minus 1. And again, we could factorise some stuff out here. We could factorise out the minus half, the x to the minus 2, because that's the lower power, and the sine x to the power of minus 2, because that's the lower power out of these, and nicely factorise it, but I'm not going to do that. What about this one? Question 4. Determine the coordinates of the turning point of y equals x e to the 2x. Now, you should know that to find a turning point, you just need to differentiate and set to 0, because a turning point is where the gradient is 0. You're either at a maximum or you're at a minimum. So, if y is x e to the 2x, I'm going to differentiate. I'm going to try and do this all in one go. So let's use the product rule because it's a product of two things. So we're going to do the x undifferentiated times the e to the 2x differentiated. So e to the 2x differentiates to 2e to the 2x. And then we add the other way around. So we're going to leave the e to the 2x alone and differentiate the x. X differentiated is 1, so it's 1 times e to the 2x. And because there's a turning point, the gradient is 0. Now what we could do here is divide both sides of the equation by e to the 2x, but you should never really divide by anything involving a variable. What we should do is get 0 on one side and then factorise out anything you can to solve. So we can factorise out the e to the 2x because that's common, and we can see we have 2x plus 1. And now, because we've got a product of two things equals 0, either this is 0, but if you think about the graph of an exponential term, e to the 2x will look like this, any exponential graph looks like that. And we can see that the y value is never 0. So e to the 2x can't be 0, so we can just strike that out. In general, exponential terms can't be 0. So that means that 2x plus 1 is equal to 0, and that means x is equal to minus half. Now it's asking for the full coordinates of that turning point, so we then need to sub in that minus half back into the original equation to get y. So y would just be minus half times e to the 2x, so 2 times minus half is minus 1, and we get that. And you could write that as minus 1 over 2e, because e to the minus 1 is 1 over e, so the e will be at the bottom, just as that 2 will be at the bottom in the denominator as well. Now going back to our original piece of paper, we've differentiated composite functions. So when we have a function within a function, we use the chain rule. When we had a product of two functions, we used the product rule. And then finally, if we've got a division of two functions, we use something called the quotient rule. So let's do that now. And the quotient rule is this, and I'm not going to prove it, but you can find it in my slides. So if you have y is equal to some expression over another expression, so u and v in alphabetical order, then dy over dx is going to be, and this is given in the formula booklet I should note, v du over dx minus u dv over dx all over v squared. So this is called the quotient rule. And the way I remember this is to think that, well, the numerator is pretty much the product rule, except that instead of a plus, we've got a minus in the middle instead. And because it's a subtraction, it does matter which way around these go. So I just remember bottoms first. So the v is at the bottom of this fraction, and the bottom, the v, is at the start of the numerator, and the v is also at the start of the denominator as well. Bottoms first. And I also remember that the denominator gets squared. So let's apply that to these last few things here. Y is equal to x over 3x minus 1. So this is the u, and this is the v. So du over dx, the numerator differentiated is just 1, and the denominator, the 3x minus 1, it just differentiates to 3, and now we can use the quotient rule. So the denominator, I said, gets squared. And then for the numerator, we do v du over dx, so v, the 3x minus 1, times d over dx, which we said was 1, and then minus, and then u, which the u is the x, times dv over dx, the dv over dx is 3, and that is it. And we can simplify that a bit to minus 1 over 3x minus 1 squared. And one very last question, y is equal to sine 4x over x cubed. So the u is going to be the top, the sine of 4x. The v is going to be the bottom, the denominator, which is x cubed. Differentiate each of them. So du over dx is, using the chain rule, 4 cos 4x. And dv over dx That differentiates to 3x squared. And then let's just use the quotient rule. So dy over dx is, well, we square the denominator. X cubed squared is x to the 6th, double, it just double. And at the top we do v du over dx, so that's x cubed times 4 cos 4x, minus, and then you do the u times the dv over dx, so the sine of 4x times the 3x squared. And then we could actually simplify this because we can see that top and bottom we could divide everything by x squared to give this final expression here.